post your question in the chat or raise your hand to ask question during the presentation. And so the translation are available. This session is going to be recorded, and we're going to share it later in our YouTube channel. So today's presentation is going to be done by Dr. Chamikara from Data 61. But before I introduce him, let me acknowledge the people of Woiwurrung and Bunwurrung language groups of Eastern Kulin Nation, on whose unceded lands we conduct the business of RMIT University, and the land that I am speaking from today. As we gather virtually across many different parts of the world, we also encourage you to acknowledge the lands in which you are joining us from. We respectfully acknowledge the First Nation people of the 5 Kulin nations, their ancestors and elders, past, present, and emerging. So today's seminar is titled Federated Learning, Split Learning, and SplitFed. So Dr. Chamikara is a research scientist at CSIRO's Data 61, and he's also affiliated with Cybersecurity Cooperative Research Centre, CSCRC, both in Australia. He received his PhD from RMIT University, Australia. So thanks, we have alumni in here. So happy about that. And he has received many awards, including Research Achievement Award for Outstanding Research Performance from our school at RMIT University. He also received RMIT Prize for Research Excellence in Higher Degree by Research. He also received Collaboration Award, Software and Computational System Program at CSIRO Data 61. His current research interests include data privacy, distributed privacy-preserving machine learning, explainable AI, and human-centric cybersecurity. So welcome, Chamikara, and I'll pass it to you. Thank you so much.
Thank you, Shabnam. Let me share my screen. Can you see the slideshow?
Yes, perfect. Thank you.
All right. So thank you, Shabnam. First of all, let me thank Shabnam for inviting me to do this talk. I am M.A.P. Chamikara, a research scientist at Data 61. I'm also honored to do this talk at RMIT, being one of the alumni of RMIT. So today, my talk is on the sequential development of SplitFed from Federated Learning to Split Learning and SplitFed. So it's a known fact that machine learning has become an essential tool that is used to generate variable insights, and machine learning models often need large data sets, especially models such as deep learning approaches. The traditional approach was to collect all the data to data centers and conduct machine learning on the collected data. And if we look at the existing domain of research, there is a massive distribution of data. For example, it has been detected that there is around 5 billion mobile device users worldwide, which is a very huge number, and this is just one factor. And according to the HIPAA journal, between 2019 to 2021, there has been more than 4,400 healthcare data breaches that has taken place. So those breaches have resulted in loss, theft, exposure, or unauthorized disclosure of more than 340 million healthcare records. So it's quite clear that the existing centralized approaches, or the previous centralized approaches for that matter, have privacy, efficiency, data distribution, and bandwidth issues or limitations. So these are not addressable by using centralized approaches. Federated learning, on the other hand, is a distributed machine learning approach that was introduced to solve these approaches. This was introduced by a research team at Google, and they published this work at AI Stats in 2017. They call this approach federated learning since the learning task is solved by a loose federation of clients which are coordinated by a central server. Now, if you look at the vanilla architecture or the basic algorithm of federated learning, as you can see in the figure, there is a server and there is a collection of distributed clients. And the server starts defining the base model at the server side, and it initializes the base model architecture and sends that to all clients. So this is a common agreement between all clients. The clients train the model in parallel through a learning algorithm such as stochastic gradient descent and update the model parameters for a certain number of epochs and send them back to the server. So these models or the model parameters sent by these clients after training them for certain epochs, the server aggregates them through an aggregation mechanism such as federated averaging. And the aggregated parameters, which you call the global model, is sent back to the clients. The clients then start training the model from that state onwards, and they repeat this step from 3 to 6 over and over again for many rounds until the model converges or the total number of rounds that has been pre-specified has reached. Now, it's very clear that federated learning solves privacy up to a certain extent. How? The clients do not share the raw data. The clients only share the parameters with the server. And efficiency is solved for up to a certain extent. And data distribution is definitely solved up to a certain extent. And bandwidth issue is also solved. Like it's always now the amount of data that you have to share is fixed up to a certain extent because you only share the trained parameters. That's a fixed size compared to sharing large data sets. So bandwidth issue is also resolved up to a certain extent. However, it has been understood that the model still is trained on user data. Hence, it releases certain level of privacy or leaks certain level of privacy because the parameters are trained on raw data of the clients. Now, the literature shows a plethora of vulnerabilities of federated learning, and there is a large motivation towards investigating these vulnerabilities as well. Now, most of these vulnerabilities come from the aspect of the model parameters being trained from the raw data. So some of the attacks on federated learning include membership inference attacks, data poisoning attacks, backdoor attacks, and free riding attacks, and there are many more other vulnerabilities of FL. So it's clear that FL doesn't solve all the problems. Now, as a solution, if we look at all the solution and try to summarize how these solutions try to solve the issues of federated learning, it's clear that people try to limit the data shared with the server. One of the ways people try to limit this amount of data shared with the server is to apply different privacy preservation approaches such as differential privacy. And also another way to reduce these effects or issues is to use complex ML structures to make the knowledge extraction process a bit more complex. Now, some of the solutions or these solutions can be categorized to different areas, basically client side, server side, as well as communication. So based on these three components, people try to solve these issues in different directions. For example, the solutions that try to solve these issues at the client include local differential privacy at the client side, and the solutions that try to solve these issues at the server side include global differential private-based approaches such as model or privacy-preserving model parameter aggregation. And there are other approaches such as one of the recently developed approaches by Google, which use secure multi-party computation of parameter aggregation. And there are other secure FL solutions as well, such as based on homomorphic encryption. Now, by looking at these issues, a research team at MIT came up with the idea of split learning. Now, split learning is originating also from the same idea of limiting the data shared with the server for enhanced privacy. And also, split learning tries to reduce the bandwidth required in transferring data between the clients and servers, as well as reducing the computational power required from the clients. And as you can see in this figure, it's a very simple architecture where the model is split between the clients and the server, where clients keep only a portion of the model, whereas server has the remaining portion of the model. Now, the motivations of SL are restricting the input data at the local devices, just like in federated learning. And data never leaves the data owner or client, just like in federated learning. And beyond that, reduces the computational power necessary for clients, or in other words, allow resource-constrained devices to conduct these computations, and also reduce the bandwidth necessary for data communications. Now, if we look at today's benchmarked models such as AlexNet, which has 60 million parameters, and VGG16, which has a total of around 138 million parameters. These are very big models. Now, computation as well as communication of these models in federated learning settings will be very, very complex. And also, like if the clients are already or with enough resources, obviously these models can be computed quite efficiently. But when the resource constrained clients are available in the federated learning setup, this can be a huge challenge. So SL tries to solve these issues. Now, the main algorithms of split learning looks like this. Now, it's a straightforward approach. As you can see here, it's the same conventional deep learning paradigm. The only difference is that we have a split of the network. Now, if you look at the situation where there is only one client, a server, the model is now split between the client and the server. So as you can see here, there is a split of the model, and part of the model runs at the client and the other part runs at the server. And the part that runs at the client is called the client portion, and the place where we have the split, we call that layer the cut layer of the client, and that the same layer at the server is called the cut layer of the server. Now, the approach is, say for example, we introduce data into the client side component. Now, once the data are introduced, the gradients are forward propagated or propagated forward up to the cut layer, and the cut layer will produce an activation matrix or matrix of activations, which we called the smashed data. So from this cut layer, the client will produce smashed data, and the smashed data matrix will be sent to the server, and it is introduced to the cut layer at the server. And then the server will feed forward propagates the gradients up to the labels, and the loss is calculated and back propagates, and in the same way the cut layer will produce another matrix of smashed data and send that back to the cut layer of client, and the client will do the back propagation. So it's kind of a two-way step broken into four-way or four steps: forward, backward. Now in this step, it's clear. Now, if there is only one client, we don't have to worry about state update of this portion. But when there are more clients, there are two modes of SL that allows updating the state of the client side model or client side portion. Now, let's look at this architecture. Let's assume that Alice 1, Alice 2, Alice 3, Alice 4 are clients, and Bob is the server. Now, in the same manner that I explained in the previous slide, Alice will communicate with Bob. And after a certain epochs, Alice will come to a certain state. Now, say Alice 2 wants to train its algorithm or train its model. So Alice now need to get the state of Alice 1. So Alice 1 will transfer its state to Bob, and Bob will transfer the state of Alice 1 to Alice 2, and Alice 2 will start from that state onwards and train itself. So Alice knows the information of Alice 1 or the model state of Alice 1 and Alice 2, and Alice 2 will be a more generalizable model. So in this way, this process continues in a sequential fashion. And in the peer-to-peer approach, they introduce the setting where you don't want to transfer the state through the server. Rather, you have a peer-to-peer communication between all the clients to transfer the state between each clients. Now, another issue of the vanilla approach is that, if you remember, now server kept the labels, or the loss is calculated at the server. So this can introduce another level of privacy issues when you deal with very sensitive data. For example, if we consider very sensitive data such as healthcare data, let's say, for example, there is a label that determines or shows whether a certain patient has COVID or not. Now, in this sort of setting, server has the capability of inferring the activations coming from the clients and seeing what label corresponds to those activations, and this would allow a certain leverage for the server to infer through activations to identify the patterns of the labels. So to avoid this, the authors show a three-way partitioning of the model, where now we, instead of two partitions, we have three partitions. So the client portion, server portion, and at the server there is another partition, right? Now here we have the cut layers, just like in the previous case. Now the loss is calculated at the clients. Now clients calculate the loss and back propagates the data and comes back to the server, and server back propagates and then back propagates. In this way, the authors have come up with different types of configurations based on the requirements. Like this is one of such configurations which allow for multiple institutions holding different modalities of user data to train to learn distributed models. For example, the vertically partitioned setting. So the idea is very simple. So the client 1 and client 2 will conduct the partition update or the portion update and come to the activation or the cut layer. And once the server receives the updates from the multiple cut layers in the vertical partition setting, it will apply merging of all the activations, and it will simply do the forward and backward propagation. And this partition is just a separation of these two. It's just a simple merge. Now, the question is, does SL solve the issues of federated learning? So in SL definitely enhances privacy because we know that now instead of keeping the entire model at the clients, SL only keeps portion of the model and it transfers only the activations to the server. So it definitely solves the privacy issues of FL up to a certain extent. However, it does not fully resolve all privacy issues. Now, which I'll talk about in the next slide. And also, efficiency is a bit slower than FL due to the sequential nature of model training, because from client to client, each client has to wait for a certain time until the previous client trains. Now, SL solves the client-side high resource requirement problem because it only keeps a portion of the model. However, SL can still leak privacy through the smashed data when the client model is too small. When the client model is too small, there is a higher chance that the activations resemble the properties of the input data in a better way than a complex model. Now, if we do a simple comparison between FL and SL, FL has no access to raw data and SL has no access to raw data. And now these green colored ones show you a bit superior setting compared to each other. Now, SL has a partial model at clients and FL has a parallel training approach, and SL provides the capability of using resource constrained clients, and SL works on lower bandwidth settings because it only has to transfer the activations. And in FL, the model convergence is faster because of the algorithm or the native algorithm that is provided by FL, which we discussed a few slides back. And FL also has a lower server burden or server computation compared to SL, because SL now has to do computations for the for a certain big portion of the network as well. But at Federated Learning server, it's basically the aggregation process, and FL conducts model aggregation where SL doesn't. Now, by looking at this, the green colored ones give you a certain intuition towards, can we identify a certain amalgamation between these two to develop a superior version? By going this direction, we came up with the concept of SplitFed, which is the amalgamation of federated learning and split learning. Now, the main intuition is, how can we identify an approach that provides FL efficiency and SL privacy? Now, we published this approach at AAAI 22, and this is titled as SplitFed, when federated learning meets split learning. Now, the basic algorithm of our approach, which is named SplitFed, is like this. Now, the figure represents the whole architecture. Now, here the clients are the split clients. They hold a split of the entire model, whereas the main server holds the remaining split related to the server side setting. And this Fed server is used to average out or apply federated averaging on the parameters of the client models. Now, the way it works, just like in the previous two settings, we first have to initialize the model, and then at each round, client models, the client portions, they start computing the client portion in a parallel fashion. And then when they reach the cut layer at the clients, they pass the smash data matrix to the client. And in this setting, the first setting that I'm explaining here, we keep a server instance communicating with each client separately, or we have a separate instance, server instance for each client. And the server instance that corresponds to this client will receive the smash data, and it does the forward propagation of the data, calculates the loss, and back propagates. And soon after it reaches that point of cut layer at the server side, the models that have reached that cut layer, altogether we calculate federated, or we apply federated averaging on all the server components. And the smash data are then passed back to the clients. That happens before the averaging part, and then the clients will do the back propagation. And once the back propagation is complete, that state is averaged out, or we apply federated averaging through the federated or Fed server, and Fed server will apply federated averaging and send back the updated parameters back to the clients. So in this way, it repeatedly conducts this until the model converges. Now, in this setting, for the experiments in the paper, we have used the label sharing approach, but the one I showed you, that was U setting, or U configuration can be applied if label sharing should be restricted. Now, we introduce two variants to our approach, SplitFed. Now, the first approach is this one. As I said, in this approach, every client has a server instance kept at the server. Now, the second approach is to avoid having many instances. We use the same instance, just like in the vanilla split learning approach, and update the clients in a more sequential fashion. However, the clients will calculate in the same way. The architecture is the same. The clients will calculate the parameters or do the computation up to the cut layer in a parallel fashion, and the data will be sent to the server, and the server will serve each client in a random order. So, and also we can find out different SFL versions beyond these two approaches, motivated by approach which were developed by other people. So, privacy of SplitFed is now definitely is better than federated learning, because we now use a split of the model, and the main server has access only to the smash data. So that's how we make sure it provides better privacy than federated learning. However, an untrusted main server has the ability to infer the smash data. Now, this is highly unlikely for a larger networks, as smash layer is far from the inputs or resembles less and less features as you move forward from the layers or larger network is. However, for smaller client-side networks, this possibility can be a bit higher. And also there is another point where federated server has access to the client portion. So again, for the federated server, it will be challenging for the federated server as it has access only to the client portion. However, these are the two identified points of leak, privacy leak in SFL. So we apply a certain privacy enhancement to the SplitFed settings. We use client-side model training with differential privacy. We use the concept that was proposed by Abadi, that is deep learning with differential privacy, which improves privacy drastically and allows us the capability of presenting differentially private robustness. And however, we have identified that now these smash data are shared between the clients and server every round. There's a certain chance that the first few rounds may leak certain level of privacy through smash data, because this algorithm, how it works is it will adjust the gradients as the algorithm goes on. So to avoid this unanticipated privacy leak, we apply another additional noise layer to the client-side model to stop this privacy leak, potential privacy leak from smash data, and providing better robustness. So we test this approach through 4 data sets as well as 4 benchmarked models. We test them on LayNet, AlexNet, VGG16, and ResNet 18 from small to large number of parameters, 60,000, and the largest one, VGG16, has 138 million parameters. And when we look at the results, it's clear that federated learning is always giving better accuracy, and the versions we have proposed or developed provide accuracy which is very close to the SplitFed accuracy. Now, in all of these settings, the split layer, we configured them LayNet at second, AlexNet at the second layer, VGG fourth, and ResNet third. This is pretty much based on where the convolutional part ends, or the 2D max pool layer is available. So this is coming from the intuitions used by the original split learning paper, where they argue the fact that the main weight of calculation comes at the fully connected module. So we went with the same intuition to make sure we have generalizable results. So the results now what you see is after 200 global epochs. And we also investigated the dynamics of the proposed privacy settings on SFL. So you can see in this color the normal plot, and as you can see, we fixed delta and epsilon at these values and changed the epsilon value of the pixel DP layer at certain values, and it's clear that for lower epsilon values we end up with lower accuracy. Now a comparison of these three would give us this sort of a conclusion, where Now SFL has inherited a lot of good properties where SFL doesn't provide access to raw data, and only a partial model is kept at the client. Use parallel training, resource constrained clients can perform better, low bandwidth is required, model convergence efficiency is close to FL, better privacy preservation than FL, and however there is a high server computation because we are still using that concept that is used by SL, at least for the server portion, although it's not exactly what's happening at SL. And also it conducts model aggregation, which gives a better performance compared to SL. And in conclusion, SFL offered better model privacy by network splitting and differentially private client-side model updates. SFL is faster than SL. Accuracy performance of SFL is similar to SL. SFL provides better privacy than FL. As future work, we intend to do a detailed analysis of the trade-off between privacy and utility, and also we are looking at utilizing different concepts like fully homomorphic encryption at the Fed server side, if in case the Fed server becomes malicious. And at this point, because the Fed server only needs to be a very simple server, because it only calculates the averaging part of the client portion, we consider that to be an edge computer or edge server for that matter. That's my talk. Hope you
Thank you so much, Chamikara.
No
now it's time for the question from the audience as well. So we have the first question from Nasreen. If one or more clients are faulty, e.g. like a crash vault, would that affect the efficiency or accuracy of the final model?
It's more of like the time taken for the convergence. So when because we went with the intermittent client dropouts. So just like in Federated Learning, we try to intermittently drop clients, assuming or to reflect the real world setting. So basically, when you drop the clients, it starts to reduce the speed of convergence or the efficiency of the convergence.
Cool. Thank you so much. Any other questions? Okay, till we are waiting for the others to drop their question either in the chat or directly, I'm going to ask you a few questions. So the first is that you were mentioning about the ability of the server when we're using the SFL to infer through the smash data. Is there any known attack for this scenario? Have anybody tried this? Is there any experiments on that?
Yeah, so basically literature shows certain attempts to attack. So that's basically our next step to investigate what level of privacy leak can occur through smash data sharing. However, to mitigate these problems, we come up with this noise layer application. So the idea is we already provide the robustness. That is limiting the output accuracy at a certain point so that it doesn't leak or enable the ability to identify outliers, so that outliers sensitivity or the privacy is leaked. So however, that investigation is yet to come. So we are still working on it.
Okay, and those leakages are coming mainly from forward propagation or the backward propagation or both?
It depends. Like there can be like just like in Federated Learning, there can be certain clients who try to poison the data, and also in a setting where now we say the server can become untrusted. That's the whole point of split learning as well. Try to share only a limited amount of data with the server. There can be certain issues coming from server as well.
Okay, so before I continue with my next question, we have another one here. Could you please give insight on the implementation with PyTorch or TensorFlow? Like, is this study available as a library so that any model could be modified to FL or SL?
Yes, actually, we have shared the code in GitHub. So if you're interested, you can have a look at it. So basically, currently we have identified a case-by-case setting where we developed or customized the algorithm for the data set, from data set to data set. we have shared the configurations on the HAM dataset, and we are now progressively updating the repository for that. So hope you would be interested and look at it.
Thank you. It would be great to share your GitHub as well in the chat, and whenever you feel comfortable to do so, they would be able to refer to that in future.
Yeah.
Thank you very much for the question and also for the answer. So again, feel free to raise your hand, ask your question, or drop them in the chat, whatever works for you. So the next question from me, maybe the last question from me, would be that I have noticed that you have done the experiment over MNIST. So, and usually the accuracy would be quite high when we are using MNIST. And what would be the possibility of using the other sort of data sets, and what would be the consequences you would believe using this model?
Yes, so it's a really good question actually. Yes, as you said, it performs well when the data set is the representation of the data set is very good. It's although MNIST is a benchmark data set, the accuracy tend to be higher. So with data sets, yes, there is a tendency of, like, we have identified for certain data sets, for, like, if I remember correctly, for Cypher 10, there was a certain instance the model even didn't converge. So this goes with the pattern of SL as well. So split learning sometimes doesn't, when for certain settings may not converge. So in that case, we need to find out the best set of hyperparameters that would suit the setting and customize the model accordingly. But based on the data set, the complexity, the model always behaves in a different way. So when the complex the data set is, the model tend to be a bit stubborn and not converge as expected. Yes.
Cool, thank you. So Haidong has a question. Is there a theoretical convergence proof different from the L1 needed?
So no, the convergence, what we have done is we have proven it empirical convergence, empirically shown it, the model converges, at certain instances, but the theoretical guarantee has not been provided in a formal setting. So we are working on those things. Like, as I said, the convergence should be done with the analysis of privacy setting as well, and how these different parameters affect the convergence. That is being investigated, and that's going to be our next work actually.
I see. Thank you so much. Any other questions? Okay, maybe I ask one more question. So you earlier mentioned about the use of homomorphic encryption. I wonder, is it an activation phase?
Not the activation phase. So at this point, we have been thinking of adding or applying homomorphic encryption only at the Fed server side, because the Fed server only has to worry about the averaging part.
Yeah, yes, correct.
But that's, it's a very good idea to look at that, application of homomorphic encryption for the activation metrics as well. But it's
there are a couple of works working on that side, but it turns out to be like quite complicated.
Very complicated.
To achieve that level of accuracy when we are moving forward to the activation phase.
Yeah.
Okay, thank you so much. Okay, I just ask the audience, is there any last question? Okay, if not, Chamikara, thanks again for accepting the invitation, and thanks everybody for joining to today's seminar. This seminar series is going to continue every month. We're going to have one seminar at the center. Mostly it's going to be online, and hope to see you in the next seminar. Thank you so much.
Thank you very much, Shabnam.
Enjoy your weekend, everybody.
Thank you. Have a nice weekend. Bye.
You too. Bye. Bye, everyone.